Hello and welcome back to another video in my Calculus 3 multivariable calculus series. Today we will be going over level curves. So I like to start off with the why and how. Why do we want to graph level curves? We want to graph level curves so that graphing in 3 dimensions is going to be easier. So a level curve is essentially a 3-dimensional graph looking down at it metaphorically. So if we had per se a circular paraboloid, which is something that I did cover in my quadric surfaces videos, if we look down at it, looking at our z is equal to z naught trace, we would essentially be looking at a bunch of circles on the xy plane. So that is why we are going to do level curves, that we can essentially reconstruct 3D graphs easily from 2D. And the how we are going to do this is we're essentially going to be doing z equals z naught traces into the xy plane. So what are we going to have? We're going to have x is equal to some function wherein we plug, z is equal to some function wherein we plug in z equals z naught. And we are going to graph that, and then we can essentially reconstruct 3D graph from that. So what are we going to do? Plot z is equal to z naught traces in xy plane. And I'll get into how we translate this into 3D more in a little bit, but let's go ahead and do an example, and we will draw the level curves of z is equal to x squared plus y squared. Little pop quiz here. What is this function? If you said circular paraboloid, you're ready for the exam already. Tell you what. But I digress. How are we going to do this? Well, we are going to... Let's start off by drawing the 3-dimensional picture so that we can get an idea of exactly what a level curve is. Well, not make it too complicated here. It's going to be a rough picture, but we essentially have a little bit too thick. We essentially have a parabola right here, parabola here, and our z equals z naught traces were like this. Okay, rough picture, but it gets the point across. Well, let's just say each of these represents, I'll shorten them down. Get rid of that one and get rid of that one. Each one of these represents different z equals z naught curves. So we'll say that this one equals the z is equal to 4 trace. Therefore, we have 3 is equal to x squared plus y squared. Okay, let's say this one right here correlates to the z is equal to 2 trace. We have 2 is equal to x squared plus y squared. Let's say this last one right here correlates to the z is equal to 1 trace. Does it look like it does? No, but we'll just pretend it does. 1 is equal to x squared plus y squared. So we have multiple different z is equal to z naughts in the form of xy. Okay? So essentially what we can do here is we can translate these into an xy plane. So if we just go ahead and do that, we have our xy Cartesian coordinates. Starting off with our first one, we will graph 1 is equal to x squared plus y squared. That just describes a circle with a radius of 1. Looks just like that. Moving on, we have 2 is equal to x squared plus y squared. Well, what is that? That is x squared plus y squared with a radius of the square root of 2. So we are just going to do that one. This one's going to be rougher. Square root of 2 is kind of hard to visualize there. Okay. And our final one we'll do in blue. We have 3 is equal to x squared plus y squared. Similar to the square root of 2 example that we just had, this is going to be the square root of 3 being the radius of our circle. So the gap between this circle is actually not as great as the gap from the first one. And that will be our level curve. So we have our z is equal to 1. We have z is equal to the square root of 2. And we have z is equal to the square root of 3. So what does this mean? This means that because we are in the xy plane, we can read this and essentially translate this back into x and y and z, the three-dimensional graph. So reading it like a topographic map, so to speak, the closer the curves, the steeper the surface will be. Meaning what? This right here is not going to be nearly as steep as this. So our z is equal to 1 trace, and our z is equal to the square root of 2 trace is going to be further away than our square root of 2 and our square root of 3 trace. So if we really wanted to, we could go ahead and, without looking at our other graph, translate this, once again I'm going to be doing it roughly, into three-dimensional. So we have our x, we have our y, and we have our z. We have this x is equal to, or z is equal to 1 trace. Let's go to our green. We have our z is equal to square root of 2 trace. And we have our z is equal to the square root of 3 trace. So we can essentially reconstruct a mini image if we just kept going and going and going, okay? Kept going and going and going, okay? This is going to look a lot like our original shape. That is essentially what a level curve is. It is essentially, it's nice to be able to reconstruct a surface in 3D given a two-dimensional surface. It can help us visualize the graphs a lot easier than we might normally be able to. That is something that is very nice. That is the level curves. Thank you very much.